Greetings, YouTube. Today I'm going to review the book, The Mathematical Tourist, by Ivars, Peterson, a snapshot of modern mathematics. And one of the things I like about this cover is that it's an actual map, and I happen to like maps, but it's got things like algebra, prime city, the fractal ocean, fractal mountains, things like that, Statland. So it actually depicts the mathematical spectrum as locations, which I thought was kind of cute, and it was very subtly done. At first, I'm like, I didn't even notice it before when I bought the book. Then I looked at it later, and I'm like, yeah, that's cool. And then, well, one of the things I found interesting about this is written in '88, and the last time I read about mathematics in any depth was around '84, '86. All right, I haven't really read math in any depth since then. I've touched upon it numerous times because I read about physics relatively frequently, though I freely admit that my grasp of math is not the greatest. So this book not only is an overview of math at that time, but it's an overview of math that's contemporary to my reading. And I didn't notice that when I bought the book. When I bought the book, it just looked interesting, so I picked it up. So I found that fascinating that the book not only covered a number of topics, but it covered some of them which I had touched on many years ago. Now, a number of these things were covered, the book covered, I had some familiarity with, because, again, I said I had read about math in the past. Talks about, like, for example, exploration, maps of different colors, which deals, like, how do you create a map with the fewest number of colors for all the different nations, which is a mathematical problem which has vexed people for a great deal of time, which was eventually proven that you only need 4. A whole chapter on prime numbers, which I found quite interesting. Dealing with the chapter on topology, which I love. Topology fascinates me. It always has. I don't have the background to fully go into it as a topic on its own. I've tried that and it didn't succeed. But reading a book aimed at your average layperson and that talked about topology, that one chapter, was quite good. Then he does refer back to the chapter he's written about later in the book. So you get a little update, as you're going, and seeing how it relates to other topics, which I also happen to really enjoy. Shadows from Higher Dimensions, which talks about how we deal with more than 3 physical dimensions in math and in why we need them and how they are used. And for example, he talks about the great book Flatland. Anyone that enjoys mathematics or just likes a good read, I recommend Flatland. It's written in a completely understandable and accessible manner. It deals with a 3-dimensional person like us having a conversation with a 2-dimensional being, a world that is completely flat, and the beings that live on it. And there was a book written years later called Sphereland by a different person, which kind of used the same style of writing to discuss how to envision higher dimensional spaces. For example, if you were sitting in a room and a 4th-dimensional sphere were to inject itself into your room, you would spot it as a little tiny sphere. And as that sphere would grow larger and larger and larger and larger and larger until it reached its maximum diameter, and then it would slowly drift, and it would slowly shrink until it disappeared as it passed through your space, because you're only able to perceive that higher dimensional sphere as a 3-dimensional object, which is, for us, a 3-dimensional sphere. So that chapter was quite interesting. There's a chapter in here that dealt with fractals, which was quite good. Didn't go as much depth as books I've read on it myself in the past. There is a book on chaos, which is also quite good. And I've read the book Chaos, which was excellent. This book, of course, this chapter can't go into as much depth, but it was still quite a good covering of that topic. There is a section in here that dealt with linear equations, which was a means of handling large pieces of data and how to find the best method to process them, like the easiest path through a problem to find a solution, and they depicted it in a 3-dimensional image, and like, okay, this is the shortest distance to get from here to here if you follow these different data points. And I never really heard of linear equations before, and that was quite interesting to me, because like geometry, there is more than one way to solve this problem, but there is one best way to solve the problem. And I really love the concept that there is more than one solution, but there is one best solution. That's one of the things I loved about geometry. I was not good at algebra because there's only one solution in algebra. If you either get it right or get it wrong, and a lot of the time I didn't understand what was going on underneath the process. There were a lot of assumptions in math I discovered when I was in school, and I never quite got some of those assumptions because I don't think they were ever shown me in a way that clicked in my head. If you don't have something presented to you in a way that your mind grasps it, you're never going to be able to get into that topic to the depth that you should. I was like that in history when I was younger, and I was like that when it came to exercise as an adult. I didn't wrap my head around it in the right way, and until I did, I couldn't understand it. So if you have an interest in math, and there are also some really nice color plates inside the book, which was really quite nice. And you also have an interest in the early use of computers, because when this was written in 1988, computers were just beginning to become really common in mathematical studies. Prior to that, most researchers were doing it longhand, because they thought that was real math. Only later did they realize that computers can not only do certain things much faster, but they can do a lot of grunt work that makes equations that were in the past kind of out of our reach because they required so much grunt work, and now it makes them much more easy to grasp. So it's also a nice little snapshot into that time period when computers were just beginning to be adopted by mathematical researchers. So overall, I really enjoyed the book. There were certain sections that were just beyond my grasp. He's discussing things, and I'm like, I think I understand what he's talking about, but he did throw quite a few formulas at you. Stephen Hawking's editor once said, for every formula you put into a book, you lose half your audience, which is why Stephen Hawking kept it down to E equals mc squared. But this guy uses a lot more formulas, some of which he explained in a manner that I did understand, and then again, he made certain assumptions about the mathematical background of the reader which were beyond me, which was, a pity, but that's just the way it is. It's not his fault that my math is a little lacking. But I definitely recommend this book. I had a lot of fun reading it. I enjoyed it. It was a nice refresher to some of the things I'd read about in the past, and it introduced a couple of concepts to me in a way that I found novel, which is good, which is one of the reasons I like to read about a topic from more than one point of view and more than one author. Because sometimes when you're coming at the same problem from different angles, you will suddenly find that one method of explaining something that just clicks for you, and that's important. Doesn't matter if everyone else in the world understands something. If you don't understand something, that's what matters. So finding the method that helps you understand that topic is more important than everyone else getting it already. So I recommend the book. If you enjoy math, or even if you have just a general interest in science, I think it would be useful to you. Go out, get a copy. I enjoyed it.